we have introduced the concept of a normal probability distribution by making sure that we're familiar with this bell-shaped graph of the probability distribution. And a normal probability distribution is completely determined by two numbers: the center, the mean, mu, and the spread, the standard deviation, measure of spread, standard deviation. Sigma squared is the variance, and the horizontal axis is a score, and for the general distribution we'll use an x. And there's really nothing more to say about a general normal probability distribution beyond these three letters. However, to do calculations, what you're interested in is translating a score to the area of the distribution to its left. Let me show you what I mean by to its left. Go like this. Get a color here. Let's say this color red. This area to the left of a given score, call it x, that area is the left tail cumulative probability for the general normal probability distribution. And to calculate that, there is an Excel function that goes like this: NORM.DIST, and then you put x, which is the score that you want to translate into a probability. Then you put mu, and then sigma, and then you put a 1 at the right end. Now we've already seen that the right end of a .dist function in Excel can either be 0 or 1. If it's 0, then you're talking about the point probability. The point probability in this picture would be the height of this line here. That height is the point probability. So and that's what you would get if you put a 0 at the right end. In this course, we're just never going to be interested in the point probability for a normal distribution, although we had plenty of interest in that for the binomial distribution, because it told you an exact probability for, let's say, the number of heads in n tosses of a p coin. But here we're always going to be using a 1. Now, that's all very well for the left tail cumulative probability, but there will be occasions where we are going to want to know the right tail cumulative probability. So let me give myself a different color here. And when I say I'm interested in the right tail, I'm talking about the area to the right of a given score. And so to get that, we base our reasoning on the fundamental fact that the total area under the probability distribution is 1. The total probability is 1. In other words, red plus blue equals 1. If I want to know blue, I solve that equation and I say blue equals 1 minus red. Blue. Now let's see if I can do a good job with my color scheme here by using black for an equal sign, and for 1 and minus, and then switch back over to red. So you have this colorful equation. Blue equals 1 minus red. And in the formulas to calculate blue, well, I should really call that, let's turn that back into blue. So I go like this, get the color editor, get a nice blue going on here. The blue is 1 minus norm.dist, and then x, mu, sigma, and 1. So this norm thing here is the same as the red one up there. but as you can see, these two will add together to equal 1. That being said, there's a third kind of question that comes up in homework 4, which is the between probability question. And I guess I'll switch back into black. So hold on a second here. So a between probability problem goes like this. They will give you, that is to say my stat lab will give you a mean, and they will give you a standard deviation. And let me change color here just for fun. We'll use orange. Oh, you know what that is? That's a test of my phone. They sent out a message saying they were going to test the phone. Don't pay any attention to that. It's not a problem. And then I get an email about it also, or something, whatever. Anyhow, I want to get this color here and talk about a between probability. A between probability problem is given by a left tail point score and a right score like this. Call this L, call this R. And then the question will be, what is the probability between L and R? In other words, what is this area here given mu and sigma? So this kind of problem will have 4 numbers. It'll have mu, sigma, L, and R. How do you do that? Well, it's still possible to do a problem like that with no new functions, because you see, let me switch color back. I want to kind of be consistent here. If I want to know this orange part, what I can do is I'll calculate the red part, which Excel can do with the formula given above, using L for the little x, and then do the same thing again for the probability to the left of R. So now I would put R for x. And so to get the orange thing, the orange area, let's switch back to that. This is so much fun. To get the orange area, orange is equal to the area to the left of R, so that would be NORM.DIST R, mu and sigma with a 1 to get a left tail cumulative, minus NORM.DIST L, mu sigma 1. And that's how you solve a between cumulative, a between probability problem. And so there are 3 kinds of problems. There's a left tail problem, a right tail problem, and a between problem. And most of homework 4 is about one or the other of these 3 calculations. Of course, you have to interpret the words and the numbers in the statement of the problem with a picture. Always draw a picture. If they're going to be talking about mu, sigma, L, and R, they will give you 4 numbers. And then you'll use this formula to calculate the answer. So we're going to switch over now to Excel and do some problems. I want to do homework 4 problems at random. So I'm going to use an Excel function to pick out 6 problems at random between number 1 and number 40, and then we can see whether I can get stuck on this. Okay, so here's how you use Excel to pick a number between 1 and 40 at random. I go like this, equal RAND, rand between, open paren, and then I say I'm going to start at number 1 and go to number 40, and I'm going to get a random number 22. Now I want to copy that formula down, so I'll go to the lower right hand corner here, and now I got these problems. Now I want to freeze these problems. I don't want to you see, the thing is if you edit any cell at all, it forces Excel to automatically recalculate the values of these random numbers. So here's what I'm going to do. I'm going to go Control-C to select those guys. Then I'm going to go to File and drop down to, I'm going to go to Home and drop down to Paste Values. See? And, okay, and it changed the numbers, and I got, I got 34 twice. That's not 6. Okay, so let's paste them again. And I think now I got them. Right. I'm looking at the formula bar up here, and that's not a formula anymore. But, you know, let me do that all over again, because I want you to see the formulas that I'm using here. So I'm going to go Control backtick and show you these formulas like this. And you see it's the same formula, but it's actually picking out different numbers. And if I go to a different cell here and put in anything, it recalculates them. That's why I have to do this copy and paste thing. So let me get rid of that. And now I got a new set again. But this set has a this set has a duplicate again. So I want to make sure there's no duplicate. That has no duplicate. Okay, so I'll select these, Control-C, and go to File. Oh, I meant go to Home, and Paste, and go down to Paste Values. And now I'll get rid of this. And now these are, you see, look at the formula bar. The formula isn't there anymore. All right, so now I have 6 different problems to do. Actually, now that I look at it, it's 7 different problems. Good luck that we have enough time to do all of them. Okay. By the way, on the right here, you see that we happen to be starting at problem number 1. So let's just take care of that and give you credit for 1 out of 40 for free. It says, what requirements are necessary for a normal probability distribution to be a standard normal probability distribution? Well, that's from the little pre-lecture I gave there. You know that for the standard normal probability distribution, mu is 0 and the standard deviation is 1. So I would say that's answer B here. The rest of these are the other possibilities, but that's... See what I did wrong? What did I do wrong? I said mu 1 and sigma 0. No, it's C. It's mu 0 and sigma 1. This is so much fun. Okay, so now we got it right. And I got a pat on the back by a robot. Good for me. Anyhow, so now we go to number 12 and see what we can do with that. Here's number 12. Okay, so here we have readings on a thermometer. So that's a random variable. They're going to read a thermometer a certain number of times. And they're going to tell us that the readings are at mean 0 and standard deviation 1, which on the centigrade scale is between freezing and 1 degree centigrade above freezing. It also happens to be the mean and standard deviation of the standard normal probability distribution, but let's not let that get in our way because we know how to use NORM.DIST. But they do say calculate the probability that a randomly selected thermometer, and so you have to imagine a huge population of thermometers. And the question is what's the probability that it reads greater than negative 2.22? But first they want us to choose which of these graphs. Well, the key is the word greater than. So that would be B, right? Because there's all three have a 2.22 in them. A can't possibly be right because the problem says negative 2.22. So it's between B and C. But C is talking about the probability of being less than negative 2.2. So it's got to be B. So we go like that. Now comes an interesting thing. In the old days, no Excel, not even calculators, but some very diligent people calculated a table of all the probabilities that we need for this homework, and they put it in a table that looks like this. It's called a standard normal probability table. And let's just see if we can get an answer from this. Notice that they're showing a green area, a left-tail cumulative probability distribution, and it's a z-score because they always use z for the standard normal probability distribution. And the way it works, look, we want negative 2.22. In the leftmost column here, you go down to negative 2.2, and that gets you 1 decimal place. Then you go over to the column for 0.02. You see that, this column for 0.02, and you get 0.0132. That is the answer they want, and it is to 4 decimal places. Let's say we're done. Now let's just see if that comes out. So 0.0132. Oops, get a 2 in there. Let's see if that comes out right. Oh, you know, very funny, very funny. You see? Let that be a lesson to you. I wasn't even paying attention to myself. What I just calculated was the answer for C over here, but we already said that we want the answer for B. But the sum of the probabilities under any probability distribution is 1. So what we really want is 1 minus 0.0132. Okay. So I'll tell you what, we could do that over here in Excel. Equal 1 minus 0.0132. And let's see what, so we get 1. But you know, that's to only 1 decimal place, and maybe we want some more. We want 4 places. So I would say 9868. Let's see what happens with that. 0.9868. Aha. Okay, so this time got it right. So that's the answer to number 12 for my numbers. Your numbers are going to be different, but now you know all the mistakes you could possibly make, okay? We now go to question 35. So I'll go down here to 35. Oh boy. Big words, lots of numbers, but let's take it one step at a time. It says that men's heights are normally distributed with a mean of 70.2 inches and a standard deviation of 2.8 inches. Then, okay, so hold on a second. Let's just deal with that one sentence, because that's the 2 numbers you need for a general normal probability distribution. We have the mean and the standard deviation, so that's one curve. Then they tell us for women's heights have a mean of 63.2 inches and a standard deviation of 2.5 inches. So that's another picture. We've got 2 pictures going on at the same time. One for men, one for women. And now they tell us a magic number. A standard doorway height is 80 inches. That's an X value. That's a score for the random variable that measures heights of men or women. So part A of the problem 35 says, what percentage of men are too tall to fit through a standard doorway without bending, and what percentage of women are too tall to fit through a standard doorway without bending? Okay, so we're talking about a right-tail cumulative probability. Why do they say that? Because they're talking about greater than, too tall. Too tall means more than 80 inches tall. All right? So let's go over here and do a calculation. So we're talking about right-tail cumulative probability distribution. Well, from the pre-lecture, that means we got to subtract from 1 the left-tail cumulative probability for the given 80 and so forth. So 1 minus NORM.DIST, open paren, we put in the 80. The mean for men is 70.2. The standard deviation for men is 2.8. And we got to put a 1 at the right end because we are dealing with cumulative. And we get this very small number here. As a matter of fact, they want it as a percentage, so we'll convert that answer to a percentage, but they want it to 2 decimal places, so we'll bounce this up to 2, and we still, oh, it's 0.02%. Let's see if that comes out right. Yes! Very good. Okay, go to B. Go to the second half of A, which is do the same thing for women. So I'll tell you what I'm going to do. I'm going to copy this down and then edit it and put in the mean and standard deviation for women, keeping the 80 the same. The mean for the women is 63.2, and the standard deviation for women is 2.5. And now we get to 2 places, it's 0. In other words, women don't really come in flavors bigger than 80 inches, much at all. So put a 0 here, and that's the end of that. Okay? Let me show you the formulas I'm using, because you always want to know the formulas. There they are. The top one is for men. The bottom one is for women. They're both right tail cumulative probability distributions because of the 1 at the right end. Okay, so we have more to do though, because, oh no we don't, that's the answer, that's 35, we just did it. All parts are showing. Oh, very nice. Oh, wait a minute, I didn't do part B. So the statistician, well, part B says, if a statistician designs a house so that all of the doorways have heights that are sufficient for all men except the tallest 5%, what doorway height would be used? Oh my gosh, this is actually over the top. We have not talked about how to do this kind of problem. So I got to tell you something. I'm going to kind of do a verbal lecture and see if we can deal with this without a blackboard lecture. So, okay. Now, they're talking about all men except the tallest 5%. So what they're talking about is what is the height of a man such that all other men are 5% above that height. 5% of all other men is above that height. So I'm trying to go from a probability to a score. I need to know a height such that all the men taller than height constitute 5% of all possible men. So that 5% is a right tail cumulative probability. There's another Excel function that goes from probabilities to scores. And that's called NORM.INV. So I'm going to go like this, equal NORM.INV. But you see, NORM.INV, just like NORM.DIST, always works to the left. That is to say, it's going to tell me the score for a left tail cumulative probability. But you see, I'm only given a right tail cumulative probability of 5%, 0.05. So if I want to get the score that has 0.05 to the right, and I can only deal with probabilities to the left, I will put a 1 minus 0.05 as my score. Then, since we're talking about men, we'll use the data for men of 70.2, comma, 2.8, close paren. And let's look at the formula before we see whether this comes out correct. Okay, so we're talking about that 95% of the men are shorter than the desired height. And the desired height is 74.8 inches to the nearest tenth. Before we say anything more, let's make sure that comes out right. 74.8. Okay, so that came out right. So what did I do? Well, I used this formula here to go from a probability of 95%, 0.95, to a score. So in other words, we shortened the doors. That's what we really did. Let's review this in another way before we go on. In Part A, with an 80-inch door, 2% of the men were able to fit over that. We're taller than that door. But we want to get 5% of the men. So we shorten the door so that more people are taller than that door. 5% are taller. Okay. There's nothing more to say about that. It's very complicated. Let me show you the formulas again for both parts of the problem. Actually, we'll bounce this down to a smaller number of places to one place, because that's the answer we used. And the formulas were in both directions. In the top two answers, we were going from score to probability for two different probability distributions. And in the bottom answer for Part B, we were going from a probability to a score for just the men, because that's all they wanted to know. They didn't ask about women, but, you know, that's my stat lab for you. They're prejudiced. All right, so let's take these away. That takes care of problems 12 and 35. And we'll go to problem 3. Let's see what we got over there. Okay, now we're back to a real simple picture. There's no story. They're giving us a z-score, which z is always the letter they use for the score in a standard normal probability distribution. And they're asking us for the green part, which is the area to the left of a z-score of 0.14. Now, we could use the tables, but it gets a little complicated, because what they do with these tables is they show you negative scores up to 0 in one table, and then they go to the other table for positive scores. Now, we have a positive score here. We have a 0.14, right? So here's a 0.1, and we go to the hundredths column as 0.04. So it's 0.5557. Let's see if that comes out. Okay, it is a left tail. Okay, 555, what did I say, 7? So that came out right, but let's do that in Excel and see whether we get a confirmation on that number. So I'm talking about equal NORM.DIST of 0.14, a mean of 0, because we're doing the standard distribution, standard deviation of 1, and cumulative, and we get 55.57, which looks wrong until you realize you want it not as a percentage, but as a decimal number, and give it to 4 places, and there's the same answer to 4 places. So that's the answer to number 3. So let's go to number 18. Okay, here we have a between probability, which I did mention in the pre-lecture. Now, if we started to use tables here, we're going to be looking up two numbers. We're going to have to be doing standardization, because we're talking not about the standard normal probability distribution. We're talking about a general probability distribution with a mean of 100 and a standard deviation of 15. So we would have to do little calculations to convert it to standard with x minus mu over sigma, blah, 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 blah. Let's do it the easy way. Just for your information, if we were viewing an example, we would be going through the standardization calculations, and then we would be doing table lookups, and lots of them, and doing a subtraction, and then blah, 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 and we would be doing all of that work. Let's do it the easy way, okay? The easy way goes like this. we're going to be doing a left tail cumulative probability for score of 110, and then subtracting the left tail cumulative probability for a score of 75. So go equal NORM.DIST, open paren, at 110. And now we enter the mean they gave us, which was 100, and the standard deviation was 15. And we do a 1 at the right end. Don't press enter yet, because now we want to subtract NORM.DIST at 75 for 100 mean and 15 standard deviation, and 1 on the right end. And we got an answer. And I think it's 6997. 0.6997. And that's how easy that is. So, by the way, this is a little interesting. That's about 2/3 of the probability. That's 2/3 of the probability. So, just to remind you about something that was talked about a little bit in class, since I'm seeing 2/3 of the probability, that reminds me of 68%. Do you remember what 68% is? 68% was the probability between the mean plus or minus 1 standard deviation. Okay, so let's get the area between the mean of 100 plus or minus the standard deviation of 15, just for fun, equal NORM.DIST of 110 plus 15 with a mean of 100 and a standard deviation of 15 minus NORM.DIST of 110 minus 15 at 100 and a 15 and a 1. And it's 58%. Why is it 58%? It's not 68%. Why is it smaller? Why is it smaller? Well, because why? Why is it smaller? Why isn't that 68%? We may have to rethink that a little bit. I really would have to go draw a picture. Did I do the right formula? Yeah, I think I did the right formula. So what is going on here? I'm going to edit this whole thing out, but, well, I can stop it for the moment. Yeah, well, I know what went wrong. What went wrong is that I should be using 100 over here and 100 over here, because it's mean. The mean is 100 plus or minus. That should be 68. There you go. There's the 68%. Sorry about that. Okay, so that takes care of problem 18. And now we move to problem 38. So let's try that. Okay. We're talking again about temperature of human beings, a mean of 98.18 and standard deviation of 0.64. And then a hospital, in part A, a hospital uses a 100.6 degrees as the lowest temperature considered to be a fever. What percentage of normal and healthy persons would be considered to have a fever? Well, that means what's the probability of 100.6 degrees being the low limit for having a fever? So we need a right tail cumulative probability distribution. So equal NORM.DIST and 100.6 is our score. The mean is 98.18, and the standard deviation is 0.64, and we're talking about a right tail cumulative probability distribution. So we have to subtract this from 1. And to 2 places we get 0.01%. Let's see if that's right. So far so good. So what we're saying is a very tiny number of people have such a high temperature of 100.6. 0.01%. So I would say this cutoff is not appropriate. No, because there is a small probability that a normal healthy person would be considered to have a fever. So I'm going to go for that. And that's wrong. No, because there is a large probability D. Go for D. There you go. There is a small probability, 0.01%, that a normal and healthy person would be considered to have a fever. And now, again, we go into a opposite question, because Part B says the minimum temperature for requiring further medical tests should be how many degrees if we want only 5% of healthy people to exceed it, instead of 0.01%. So again, we're going to use NORM.INV because we're going from a probability to a score, to a temperature. Okay, so that means we want 95% of the people to be lower than 100 lower than whatever this score is that we need. So, okay, so I'm going to go equal norm.inv 1 minus 0.05, and then we'll get 98.18 and 0.64. And now we get a lower temperature that we're going to call the cutoff, because more people are going to have a high temperature. And they want it to 2 places. So let's bounce this down to 2 places, 99.23. And that's the end of that question. Let's take a pause here. Okay, so that takes care of question 38, and we go to question 36. Okay, we're talking about a design requirement for an environment which must fit the range of people who fall between the 5th percentile for women and the 95th percentile for men. In designing an assembly work table in this environment, the sitting knee height must be considered, which is the distance from the bottom of the feet to the top of the knee. Okay, we should really draw a little picture for this. As a matter of fact, you know what? I'm going to switch over to a lecture to draw a picture of this problem, because it's not adequate to just talk about it. I'm working on problem 36 in homework 4 about a design requirement for designing an assembly work table. And so the picture would be something like this. Let's get a nice color here. You have a desk and a chair, and someone needs to sit in the chair and be comfortable with regard to their knee height. And so they want to use a random variable that measures knee height. So the knee height they're talking about is roughly this distance here, if a person is sitting in the chair. And they say this random variable has a mean of, for men, 21.6 in my numbers, and a standard deviation of 1.2. These are both measured in inches. And they also have measurements for women, so we'll put an M on this to stand for men. And for women, they're talking about 19.5, and the sigma for women is 1.1 inches. Okay. And now they talk about issues to do with redesigning this table, work table. So they say, what is the minimum table clearance required to satisfy the requirement of fitting 95% of the men? So they're talking about this height here as being unknown, and so we draw a normal probability distribution because the problem says that these are mean and standard deviation of normal probability distribution. So let's talk about 95% of the men. So here's the men picture, and the mean is 21.6. and the standard deviation is 1.2. So when they say what is the minimum table clearance required to satisfy the requirement of fitting 95% of the men, what they're asking for is a table clearance, let's call that X. They want a value of X such that 95% of the men have a knee height less than or equal to X. You want this height here to fit inside of this height here. So let's use a little color here and say that they want to know the value of X such that this red area is 0.95 and X is unknown. Now, I've emphasized in many ways, starting with the front of the Cooper Excel in Statistics textbook, that the two basic directions of inquiry are going from score to probability and from probability to score. That's on the front cover of the book. Now, we know at this point that going from score to probability can be done with NORM.DIST. Going from probability to score is calculated with NORM.INV. And of course you have to know what to put in between the parentheses to use these functions, and we'll get to that. In this case, we're trying to go from a probability of 0.95 to a score. So we're going to use NORM.INV. So what numbers do we put in? Well, the thing is, the red here is a left tail probability, so it's kind of real easy. We'll use NORM.INV with a 0.95 probability, a mean of 21.6, and a standard deviation of 1.2. That should answer part A. Now I'm going to type that in to an Excel spreadsheet over here right away, and I'll tell you what it says and then tell you if it got the right answer. 21.6 and 1.2. And so we're supposed to get a height, and I get 23.57 inches. To one decimal place, that's 23.6. Let me see if I get that right. And I'm going to redo this with different numbers in the next part of the video. But anyhow, let's see if we get this right. Yes, we did. Okay, next part. Determine if the following statement is true or false. If there is a clearance for 95% of males, there will certainly be clearance for all women in the bottom 5%. Well, we can draw a picture to deal with that a little bit, because it's kind of silly in a way. Suppose we put the women picture down here with a mean of 19.5 and a standard deviation of 1.1. And we got this answer for the men of 23.6 inches. So that's, let's say that's over here. Now the bottom 5% of women, that's going to be over here, where this area is 0.05. And so obviously that number is way to the left of that number. And it's very simple. Answer D to this problem says the statement is false because the 95th percentile for men is greater than the 5th percentile for women. Well, the statement is true because the 95th percentile for men is greater than the 5th percent for women. So it's for me, it's A. And like I said, I'm going to redo this, and we got that right. And then the next part of the problem says the author is writing this exercise at a table with a clearance of 23.5 inches to the floor. So the author has a 23.5 clearance here. And then the question is what percentage of men fit this table? Okay, so now we go back to the diagram for men, and 23.5 is approximately here, let's say. And then, so the question is, what is the probability of having a knee height less than or equal to 23.5? Well, that's going from a score to a probability. So I go equal NORM.DIST of 23.5, 21.6, and 1.2, and cumulative. And let's dial that in and see how that comes out. Equal NORM.DIST 23.5, 21.6, 1.2, and a 1 at the right end. And I get to 2 decimal places as a percentage, and that's where we have to convert the decimal answer into a percentage and give it 2 places. I get 94.33, and let's see if that comes out right. Yes, it does. And then the question is what percentage of women fit this table? Well, so we'll take the formula that I just used and change the mean and standard deviation to 19.5 and 1.1. Hold on. And the answer is 99.99%. Let's see if that works. And the answer is sure it does. And now it asks the final follow-up question. Does the table appear to be made to fit almost everyone. And then A says the table will only fit 1% of women. Well, that's not true. It fits 99.99% of women, so it's not A. And then B says the table will fit only 6% of men. No, that's not true. It will fit 94% of men. And then C says the table will fit almost everyone except about 6% of men with the largest sitting knee heights. Well, okay, they get that 6% because 94.33 rounded off to 94% of men, it will fit them, but then the remaining 6%, 100 minus 94, will not fit. And so I'm going to go for answer C, and that's the end of that problem, number 36. So at this point, I'm going to stop recording in this computer. I want to do problems 36 and 20 with a different tool that is available to you on the cognoscitypress.com website. There's a file called Hw4.3plus.xlsx, and it's a cheat sheet that does an enormous number of problems involving left tail, right tail, between probability for normal probability distributions. And I'm going to go through this in a little bit detail, but we did draw pictures for this, and I just want to show you how to take the numbers from the problem and put them into this cheat sheet. Now, the numbers are different for this particular version of the problem, so let's see how it goes. 5th percentile for women, 95th percentile for men, okay. So for men, we have a mean of 21.9. So we'll put 21.9 over here. And a standard deviation of 1.3. 1.3. And we'll deal with the females in a little bit. But it says here, what is the minimum table clearance required to satisfy the requirement of fitting 95% of men? Okay, so the left tail probability is 0.95. So we put that in there, and we get a left score of 24.04, and they want it to one decimal place. Let's see how that comes out. Let's call it 24.0. And that worked out. Fine. Now, if it clears 95% of the men, and the women numbers are not only smaller than the numbers for men, but they're talking about the bottom 5% of the women, well, that's got to be far to the left of the bottom 95% of the men. And so it's got nothing to do with outliers. The statement is true because the 95th percentile for men is greater than the 5th percentile for women. Yeah. Okay, there's that. Now they want to talk about the author with a clearance of 23.9. What percentage of men fit this table? Well, we still have the men data up here, mean and standard deviation, but we now have a left score of 23.9. And so what percentage of the men? 9.9380, and they want it as a percentage. So we'll convert that to a percentage and give it 2 decimal places. And I get 93.8. And that's right. And now what percentage of women fit this table? Well, we'll keep the 23.9 because that's the same table for men and women, but we have to change our mean and standard deviation. For the women, the mean is 19.3, and the standard deviation is 1.2. And so we get 99.99% of the women. And there you go. And does the table appear to be made to fit almost everyone? Well, it says, let's say, it's going to be A, because you see, we got, for the men, we got like 93.8% of the men will fit under this 23.9 inch table. So round that off, that's 94% of the men will fit. And so it will fit everyone except 6% of the men. So that's question part A here, and that's the end of that. So that's number 36. Now we'll go to number 20. Take a look at that. So here we're talking about a mean of 100. Mean of 100. A standard deviation of 15. And here's the question. Calculate the probability that a randomly selected adult has an IQ between 85 and 115. Well, that's where we use the Z and the ZZ. I think this should have been called X and XX, because Z usually is used for the standard normal probability distribution, and this is not standard. But anyhow, okay, so on the left we got 85, and the right 115. And now let's be real careful here. We're talking about a decimal number, not a percentage. And we are talking about a between probability of 0.6827. Now that's 4 places. 0.6827. And then we're done. That is the 6 example problems that cover an enormous amount of different problems in homework 4.